Welcome back to our augmented STEM classroom. I'm your educator, and today we are going to be drawing our way through the incredibly fascinating world of chemical transformations. You know, if you're gearing up for your board exams right now, you already know that chemistry isn't just about memorizing a textbook. It's really about seeing how the entire world fits together and, sometimes, exactly how it breaks apart. In this explainer, watch as we use our digital pen to map out the exact mechanisms behind the most important chemical reactions you absolutely need to know.
Here's our roadmap for today. We're going to start with simple combinations, move right into decomposition, explore some chemical swaps, and finally, look at some solid surprises and essential memory tricks to help you ace those exams.
Section 1. Welcome to chemical reactions. Let's set our goals, because chemistry is quite literally happening all around you every single second of the day. By the end of our time together today, you're going to be able to confidently identify and write out these core reaction types for your exams. The goal is for you to look at a chemical equation and instantly know, that's combining, or that's decomposing, or they're swapping partners, and know exactly what is happening with the energy in that system.
To truly master this stuff, we're going to use a super simple 3-step framework for every single reaction we study today. Step 1. Always find your reactants and track them directly to the products. Step 2. Trace the energy changes. Is heat going in or is it coming out? And Step 3. Identify the final physical state of your products. Did a solid precipitate form? Did a gas escape? Keep this framework locked in your mind.
Section 2. Combination and energy changes. Let's grab our neon digital pens and jump right into our first major reaction type, the true building blocks of chemistry.
Imagine snapping 2 Lego bricks together. That's basically a combination reaction. 2 or more reactants combining to form just a single product. The general formula is simply A plus B yields AB. A classic real-world example, and one you are definitely going to see on your board exams, is making slaked lime. Watch as I draw the equation out here. We take solid quicklime, which is calcium oxide, add liquid water, and they combine to form a single product, slaked lime, or calcium hydroxide. And this actually brilliantly illustrates a key chemical concept, because this specific reaction is incredibly hot. It releases a massive amount of heat, which is exactly why this mixture was traditionally used to create whitewash for painting walls.
Since that slaked lime reaction released so much heat, it brings us to a massive distinction you absolutely have to know: exothermic versus endothermic reactions. On the left, exothermic reactions are your heat producers. Energy is literally exiting the system. Natural gas combustion, burning coal, and even your own bodily respiration, where glucose meets oxygen to give you ATP energy, those are all exothermic. Now, on the right, we have endothermic reactions, the heat absorbers. These require energy to even happen in the first place. A perfect everyday example of this is cooking an egg. The raw egg has to absorb the heat from the pan to undergo those chemical changes and actually cook.
Section 3. Decomposition. So, if combination is all about bringing things together, what happens when we need to tear them apart?
On your screen, you'll see our starting point for a decomposition reaction. We have a single unified compound. Let's label it AB. Left totally alone, it is completely stable.
But to force this stable compound apart, we've got to add energy to the system. Think of this energy like a chemical sledgehammer, coming in one of 3 main forms: heat, light, or electricity.
And just like that, once that energy is applied, the chemical bonds just snap. The single reactant fractures, leaving us with multiple distinct, independent products, A and B. This right here is the core engine of decomposition.
Let's draw out the 3 specific types of decomposition you need to memorize, starting with thermal decomposition. This is when intense heat literally cooks a compound until it breaks down. The classic syllabus example? Limestone, or calcium carbonate. When you heat it strongly, it breaks apart into solid calcium oxide, our old friend quicklime from earlier, and carbon dioxide gas. Next up is photodecomposition, and this one is driven by light energy. Look at the formula being traced out here. Silver chloride breaks down into silver and chlorine gas the moment it's exposed to sunlight. This is actually a fascinating reaction because it's the exact chemical magic they historically used in early black and white photography to capture images. How cool is that? Finally, we have electrolytic decomposition. Here, we use a literal jolt of electricity to split liquid water into its base elements, hydrogen gas and oxygen gas. By passing a current right through the water, we're providing enough energy to break apart those super strong H2O bonds. Section 4, the Great Chemical Swaps. Moving right along in our lesson plan, we are entering the highly competitive and honestly sometimes aggressive world of chemical displacement.
Think of a single displacement reaction as a hostile chemical takeover. The rule of the jungle here is that a more reactive element will forcefully kick out a less reactive one from its compound. Let's look at this classic lab experiment. Step 1. You drop a standard iron nail into a bright blue solution of copper sulfate. Step 2. Because iron is higher up on the reactivity series, it aggressively displaces the copper. Step 3. Boom! The solution transforms from blue to a pale green iron sulfate, and if you pull that nail out, you're going to see it covered in a rusty brown coating of displaced solid copper.
But in a double displacement reaction, like mixing barium chloride and sodium sulfate, it isn't a hostile takeover, it's a mutual exchange. The two compounds basically just swap their ions. Barium pairs up with sulfate, and sodium pairs up with chloride. This type of reaction often creates a brilliant solid surprise that drops right out of the liquid, known as a precipitate, like the sudden formation of this solid white barium sulfate.
Section 5, Solid Surprises and Formulas. Speaking of those solid surprises, let's lock in some crucial formulas and visual cues that you absolutely have to have memorized.
I'm writing these core formulas in bright neon so they really pop in your notes. First, standard combustion. Carbon plus oxygen yields carbon dioxide and heat. Next, the combustion of methane gas. CH4 plus 2O2 yields CO2, water, and heat. Now please pay special attention to the difference between calcium hydroxide, which is slaked lime, and calcium carbonate, which is limestone. Exam boards love to try and trick you by mixing those two up.
Okay, the crucial point here is knowing your precipitates. When insoluble solids settle out of a liquid solution during a reaction, they give us amazing visual cues. If you mix two clear liquids in a lab and suddenly a bright opaque yellow solid forms, you're likely looking at lead iodide. If it's a pure white precipitate, think barium sulfate. And if it's a chalky white solid, that points to calcium carbonate. Memorizing these colors is going to save you immense time on those multiple choice questions.
Section 6, Misconceptions and Tricks. Before we wrap up this explainer, let's clear up a major hurdle that consistently trips students up on test day. Here is a super common misconception, assuming displacement and double displacement are basically the exact same thing. Do not fall for this. The scientific reality, as we've explored, is totally different. Single displacement is a hostile takeover by one stronger element. Remember the iron nail and the copper? Double displacement is a peaceful two-way exchange of ions between two compounds, like two dancing couples simply swapping partners. One is a takeover, the other is an exchange. Keep them straight.
I want to leave you with this challenge today. Chemistry isn't just ink on a digital whiteboard. It is the actual fundamental machinery of our universe. Take these concepts off the screen and out into your real life. Look around your home today. When you see an egg cooking or you notice rust forming on a bicycle chain that was left out in the rain, stop for a second and ask yourself, which specific type of chemical reaction am I actually witnessing right now? Keep observing, keep questioning, and I promise you, you'll find that mastering chemistry is really just a matter of learning how to look at the world.